So this session, there will be 4 speakers, and they will have 20 minutes, including questions. I would like to welcome the first speaker, Karen Golden, here from Imperial College, who will be talking about effects of psilocybin on medial prefrontal cortex in behaving mice.
Okay, so like it was just introduced there, my name is Karen Golden. I'm a PhD student in the Chatterton Lab in Imperial. My main work is looking at the neuronal activity in the medial prefrontal cortex in mice. And at the moment we're doing a collaboration with Robin looking at the effects of psilocybin on the prefrontal cortex and seeing how that correlates with behavior. So I'm going to dive right in and kind of show you how we're investigating this. So we've got mice on a behavioral setup that's set up for analysing working memory. So we've got mice head fixed here into the treadmill. And what happens is that the mice go to the start position, and so you reach the start position to get an auditory cue, and this means that they run to either feature 1 or feature 2, which are tactile features, which you'll see in more detail in a minute. And once they reach that feature, they receive a reward of water through a liquid which is placed in front of them, which you can see here. Now, like I said, this is a working memory setup. However, currently we're training the mice, so the data you're going to see is not a working memory task, but it's simply mice behaving on this task and licking and running, etc. So this video should hopefully make it a little clearer. So you see the mice passes the start position. Then he goes to feature 1. In this case, once he reaches feature 2, he sees a reward to the liquid, and then he takes the water. So what we're recording during this is recording the position of the mouse in the treadmill, so by that we can correlate his speed, any kind of periods of inactivity, etc. And we're also recording the licking bouts at the detector here, so that will tell us about any false positives and when the mouse is expecting to get the reward. So these mice are very motivated. They're under water restriction, which means that their main water source is coming through this task. So you see they generally tend to complete an awful lot of trials in a given session. So this is an example of the type of data that we receive or that we get from these type of tasks. So you see here we've got a trajectory plot. We've got the position of the mouse on the treadmill and the time on the x-axis. So you see that every time the mouse reaches 90 centimeters, that's the end of a trial, and it begins again. So feature 1 is located at 30 centimeters, and feature 2 located at 50 centimeters. And what you can see here then is how we correlated the licking data. So this is where you've got trials 1 to 47 and the position. And what the heat map shows is the frequency of licking for a given position on the treadmill. So you can see, even though this is the early stages of training, the mouse has already learned that it's basically only worth its while licking at either of the features, so either 30 centimeters or 50 centimeters. Now, what we would like to do is take our control, so record this type of recording in a neuronal behavior mouse, and we also want to correlate this with the neuronal activity. So to do this, we need to take population recordings. So in order to take a population recording, the first thing to do is to perform a craniotomy, which you can see here. So you get a rectangular window onto the medial prefrontal cortex. And then we insert this probe, which you see here, which is a 4x2 tetrode. So what that means is that it's a 4-shank probe with 2 tetrode configurations, which is the 4-channel configuration you see here. And we insert that into the medial prefrontal cortex, and this allows us to actually see the neuronal activity. So this is a short video of the mouse behaving while we're actually recording the neuronal data. So an example of the kind of data we get from this is shown here. So this is an anesthetized recording, but this is simply to show you that we can record from 32 channels simultaneously. The color codes indicate specific tetrodes, and the things that we can take out of it is that you can see you've got some big depolarizations, and you've also got some action potentials here. So you can look at the unit activity and also the different type of oscillations going on in the prefrontal cortex. So to look at what we actually want to achieve, to give you a fair comparison, I'm going to first show you the behavior of a normal behaving mouse. So these are the 5 treadmills we have running in parallel, so it's essentially to speed up the training process. What we see in a moment then is the behavior of a mouse here, He's very motivated. There's a lot of kind of tail wagging, and he's basically very active. Then we injected psilocybin. So we gave a dose of about 0.4 milligrams per milliliter, and what the resulting behaviour after that was this. So basically, very long bouts of inactivity, very wide kind of stance posture, very limp movements, clearly not very motivated, because you see it's all tricky at the start position, and quite frankly you couldn't care less really. So we can clearly see by this mouse that there's a very obvious behaviour difference once the psilocybin has been injected. And even in terms of the number of trials that they completed, I mean, it's nowhere near what they were doing before. So what we wanted to then see was, okay, so what changes in the neuronal activity? So when we were looking at, say, papers that I've looked at this before, this is presented by Nutt earlier on today. So this is a paper which showed that in an anesthetized mouse, in the prefrontal cortex, the local field potentials, they were very rhythmic and quite prominent, and they actually decreased and became more broken. And you can see this in the power spectrum here, where particularly around the theta oscillations, they decrease massively once, sorry, this is hallucinogenic DOI that was injected, I should have mentioned that. And then once they injected the antagonist of this hallucinogenic, it was completely restored. So we were expecting basically these oscillations to decrease in power. And what we found was directly the opposite. Now this is very preliminary results, we're still investigating them, but what you see here is the top trace, the red trace, is pre-psilocybin injection. So this is the neuronal activity in an awake mouse, which is a very key difference to the previous results, and the previous result was an anesthetized mouse. And you can see there are theta oscillations, but they're very broken, they're disjointed. But then when psilocybin is injected, they become far more rhythmic. And these bouts are much more prolonged. So what you're seeing here is a snapshot of about 6 seconds of data. But what we did was to make sure that this was not, say, just evident in a small portion of the data. We took 20 minutes of neuronal activity, say, pre-psilocybin injection, and 20 minutes after psilocybin injection, and we performed a power spectrum. And what you see here then, again, the colours are the same, but you see that post-psilocybin injection, there's a much stronger theta oscillations. There's a much higher power in the spectrum. You can see that more in the expanded plot here. So this really shows that, this is giving us the indication that these theta oscillations are becoming more dominant. So then we were trying to look at, okay, well, where are these theta oscillations coming from? What's the source of it? And there's been quite a little bit of literature that's actually looking at these theta oscillations in the prefrontal cortex is showing functional connectivity with the ventral tegmental area and also with the hippocampus. So this is a paper by Fujisawa, which looks at the oscillations during a working memory task. And you see in the prefrontal cortex, you've got very prominent theta oscillations, very prominent theta oscillations also in the ventral tegmental area, and there's a strong level of coherence between the two. He also related this to the hippocampus and showed that there is strong coherence with the oscillations in the hippocampus, and then also the Jones paper showed as well that the hippocampus, the theta oscillations in the hippocampus and those in the prefrontal cortex were highly coherent during spatial working memory tasks. So what we would like to do is, first of all, correlate the behavior we have with the electrophysiological data, but then also kind of maybe pursue this more and to see in a spatial memory task, is it relating to the running epochs, or is it specific to when the mouse is making a decision, which is more so related to the Jones's work. So the future experiments that we're looking at, well, first of all, we need to perform more experiments to see if this is significant and see if it's characteristic all the way through. We also want to see if it's dose dependent, because the dose we gave, it's certainly on the higher spectrum of the dose, so we want to see if that has an effect. And then, like I said, then we want to see, is it correlated with locomotion? So, for example, in the hippocampus, there's very strong theta oscillations during the running, so we want to see, is it the case where just during the running periods then these sleep oscillations become more dominant, or is it present throughout the rest of the oscillations, or throughout the rest of the behavior? So yeah, so that's it. So if you have any questions, I'm happy to.
May that be that these animals are not having a very specific reaction on a specific receptor level. It is more, it could be an idea that they lost their conceptual knowledge of what to do in a more general sense, which is known from monkeys as well as humans.
Sure, yeah. Well, I mean, the thing with this task is that, so the motivation of the mouse moving and performing the task isn't the fact that he knows that when he's on this treadmill he needs to run. All the mouse is thinking is that he wants water. That's it. Because he's under water restriction, he's high motivation to do that. And in terms of understanding the concept, I mean, what I was showing with the external cues, I mean, it's more the fact that he's ignoring that that's happening. So I think it's less, say, I don't think it's the fact that he's forgetting what he has to do, because I think he's motivated to do it anyway. He's just, I guess, it seems at least that he's losing awareness of the external environment more so.
I presume the drug has no effect on motor coordination or muscle strength.
Not that I'm aware of. Well, I mean, in terms of, obviously his gait is significantly different, and how he's moving, so, but I guess my main focus with the prefrontal cortex is his motivation to do, well, not his motivation, but his ability to do the task and that, so certainly, I mean, it could affect the
Right. Your results with the decrease in theta, I was wondering if you might comment on and compare them with the results from Jesse Wood in 2012, which show decreased theta with DLI and freely moving rats.
Okay, yeah, well, so that's I guess where it emphasizes that we're very preliminary in our data. I mean, like that, those decreased oscillations, I mean, that's based on a lot more experiments than what we've done. So I mean, I'm certainly not saying that this is definitely always the case where you've got increased theta oscillations, because this is one experiment. It could easily, I mean, I don't know the details of that one, so I don't know in terms of, I mean, if they're both awake, you essentially you're getting rid of the anesthetized kind of caveat. But yeah, I mean, certainly that would, I mean, if this continues to be true, that would directly challenge that idea. But I certainly wouldn't claim that yet.
There's time for a couple more questions if there are any. Okay.